Well, welcome back to our class on system engineering. We're continuing through our second major section in this focus of the course. And for what we're doing now is we're going through this more detailed view of the design and integration process. We've done an introduction, overview, introduced some things that maybe you hadn't thought of that might be relevant to system engineering. We went through the requirements in defining the design problem. We then talked about the functional architecture development, and now we're going to get into the physical architecture, but we're getting into more details of what a design would look like. And so we're going to go through this theoretically, and then we'll be showing a variety of practical examples of different types of systems that are out there. And hopefully, as a result of that, maybe that'll give you some more perspective on how this could work for you and what you're trying to accomplish. So in this chapter, the focus is an introduction to the distinction between the generic and instantiated physical architectures. One of the things that the author uses is this concept of a morphological box to demonstrate the generation of multiple instantiations of a physical architecture. There's other ways that you can be doing this. I like to be thinking of this in an analysis of alternatives. And so you want to have a trade space that you can be thinking from one scenario, one possibility, another. But we'll still walk through this in a general sense for what a morphological box is all about. They also have a discussion of the graphical representation of the physical architecture in the textbook, and we'll follow along with that. And finally, we'll be talking about the fault-tolerant architectures. And so we have talked already a little bit about fault processing, and so now we'll get into a little bit more details. And so basically, we're having this process. And there's additional steps. So we start with the requirements that flows into a functional architecture. So you have things set up as a block of, at least at a functional level of a block. And now we're getting more into the physical architecture, and we're being more definitive about how things are going to be broken up. So physical architecture of a system is a hierarchical description of the resources that comprise the system. This hierarchy begins with the system and the system's top level components and progresses down to the configuration items, the CIs. The CIs can be hardware or software elements or combinations of those. And so we'll see some examples of how that would work out. We're going to be bringing in some of our other textbooks here as we start to develop some ideas and some different examples. And so here is a flow from the Practical Guide to SysML. And so this is a surveillance system package example. So at a top level package, it is a model, shows a packages of the next level of a model hierarchy. And I believe that's in this, we'll be capturing some of those details in these next couple of slides. The packages often contain sub-packages that partition model elements into logical groupings. So here, once again, it's not even Booty, it's another textbook. They talk about this partitioning. So you want to have clear distinctions. You want to cover anything. You don't want to have any overlapping elements in part of their functionality. So well-defined model organization is important as model elements increase, and shows a nested package structure by contrasting a structure with a similar flattened model. And so we'll be seeing some of these figures over the next handful of slides. And so you want to have non-overlapping partitioning of elements. It's okay to have a nested packaging structure. So we're starting to see a tree structure, if you will, and we've talked about that before. And we can be thinking about, well, you can have a fairly deep tree, or you can have a more flattened model. And so there can be trades from one to another. And those are things that you could be considering as you start to develop a design. So for the surveillance system hierarchy, it's organized based on an architectural principle that requires a logical architectural package, a physical architecture package, and a use case set of packages. It also contains an analysis package for various kinds of analyses and their outcomes. So here we're seeing the surveillance system. Here we're seeing these other things that are relevant. So here we have a package diagram that's showing a nested approach. And so for the camera, there's various things that are fed into that from a behavior point of view. And so you can have behavioral type of diagrams. You can have parametric diagrams. And so that would be another. And you're also going to have structure. The block definition diagram, the internal block diagram, and things like that. The surveillance system package. And so here we're starting to be showing the way that one possible way of constructing what this surveillance system would be. And we have these folders, and then there's capabilities in each of those subfolders. And so this would be an example of what you could consider for a flat package hierarchy rather than what we're showing here as an alternative. For the physical architecture, we also want to be thinking about the model package organization. And we'll be doing this in class as we start to explore in detail these different models. And you're creating not only the views, but you're creating this database. And so we have all of this rich structure of relationships and entities that are here. And so what is trying to be shown here is a surveillance system. And you could see different ways of how you might want to be organizing this. So here you have the components, you have the products. The products is broken out in more detail. So we have the camera, the requirements, the network, and the system, and other types of things that are all captured as part of that database of information, which is shown graphically in the various types of SysML views. So this is once again referring to what they're having in the practical guide to SysML. So here is another textbook that we will be focusing on, and we actually will be leveraging the DelSat 77 model that the Delgado made for this, and this is SysML distilled. And so here is a sample package diagram for this DelSat 77. So we can see how there's elements in the behavior, the structure, there's requirements. All of those things are important. And we can see that there's a tree structure that within the domain, there's a structure, there's a relationship there, and other things that are leveraged. So this is just a sample of the package. And if I was to open up the model that they have, that you can open up in Cameo Systems Modular, the demonstration mode of that, or Enterprise Architect. Those are examples of a couple of places where you could open that and play with it. So let's talk more about the physical architecture. It provides a system resources to perform functions, the hardware, the software, the facilities, the people, and the procedures. For the generic physical architecture, we have a description of the partition elements of the physical architecture without any specifications of the performance characteristics of the physical resources that compromise each element. So we're just getting to this next level of detail. For an instantiated physical architecture, we have a generic physical architecture to which complete definitions of the performance characteristics of the resources have been added. So this is where we're getting that added detail in that example. So we've talked about the F-22 and its physical architecture, and you might recall this diagram that we showed that we're really focusing on the vehicle, and in the vehicle we have the avionics, the utilities and subsystems, the cockpit and vehicle maintenance system, and it's really the avionics that we have focused on mostly for this type of diagram and how we're trying to lay out the physical architecture. Another elements that's important for as we're starting to figure out an architecture is a work breakdown structure, WBS. And this is showing an example of the elements and related life cycle phases. And so this is still related to, say, what we were just showing here for an F-22. And so we have the vehicle, so it would be an air vehicle. We have the system engineering and program management. that would be an element that you would have in the WBS. You have the testing and evaluation training, the data, and other things. And so there's various ways of how you can organize a WBS, but this is showing you how you could be doing this, thinking all these different elements. And then we have this other field that talks about where each one of these is relevant. So an operational phase, this would be later in the whole process of doing things, development. These would be the front end things. So we have a mixture of operations, development, training, manufacturing, etc. And moving on, so here are some other things and other elements for generic air vehicle. And so this is just a listing of those. And so just some more things that you could be considering. Automatic flight control, navigation and guidance, communication, identification, all of those things are examples of what would be important. So for the elevator example, here is a generic physical architecture for an elevator. And you can see how we have the top level system, the elevator system, and then we break it down into these 4 next level, the passenger interface, elevator car, the control components and maintenance. And then we're showing most of the details in terms of the breakout in the elevator car and also the passenger interface, and it goes down multiple levels. So we're seeing this tree structure starting to be made apparent with the generic physical architecture. It doesn't show any specific details, so it still is a generic physical architecture. So what is the physical architecture development process? I created this document to show what this could look like if you wanted to put it in SysML. And in the next chart, we'll have an IDEF0. So basically, a lot of times it starts out with a brainstorming function. We have to be figuring out what exactly that you want to be doing. Then there's a proposal for a physical architecture. And once that is started to figure out, you can analyze the proposed physical architecture. And if you then see that this makes sense, then you could select the final physical architecture. So those are some of the general steps. We have some other inputs, the ConOps, the physical architecture changes. You want to make sure that you capture that. And that would be things that would be influencing what you might have. There may be some other influences that are directing how things need to be done. And then for an IDEF0 point of view here, we're showing how that would flow. Basically what I already talked about, so I won't talk about that in detail. So we have the possibility of different ways of doing functional allocation. And so there can be a 1-to-1 and an on-to type of relationship. And so you can maybe have functions that 2 or more could have a connection with a single component. You can see that. And here are some other possibilities. And then below here, it's a 1-to-1 is what we're showing in detail. Okay, well, we talked briefly about a morphological box. And so here is just an example of saying we have a handful of types of possible things that we're going to be dealing with. And so the handle size and the type of material, the striking element, the weight, and having the ability or not to have nail removal. Here's an example of a hammer, maybe one that might be slightly different than one that you're familiar with. The last handful of years, I actually bought one like this, and this is actually a roofing hammer. And so there are some more specifics about the type of thing that you would want to have that hammer do. So this has a longer handle size, and so it gives good more ability for you to be creating more torque as you're trying to hit a nail. And so the longer it is, that the more that you're going to have. And so, but here's sort of like our trade space. And so if you wanted to be having an analysis of alternatives, if you wanted to think of it that way rather than morphological box, here is our trade space that we're trying to figure out. So here's another example for morphological box. This is a lot more complicated for an auto navigation support system. And so here we have the direction support, localization, the type of processor, the user input and output, and other system interfaces. And we have examples from 6 different manufacturers, and we can see where some of those things lie, that some of them have 4 of those manufacturers have those capabilities. Others have only 1, and there are examples where there aren't any at all. And so we can be seeing if we want to be doing a trade for what would represent the things that matter most to an individual application, these are the things that we could be considering. Just for illustration, it doesn't represent one of these, but I just put an example of a Garmin receiver showing how this functionality might look like. So we can have a pairwise infeasibility and feasible combination within a morphological box. And so here we can just start to relate what are the possibilities that we could have. And so once again, we're coming back to this, say a 22-inch hammer, a larger hammer, and different features like the angle removal. Is it angled or is it straight? This is pretty much straight, but this is just an illustration of a picture. And so we can see the relationships going from one to another. And that might be a helpful way of thinking about that. So ultimately, doing the analysis of alternatives, you can be coming up with metrics, coming up with a handful of key performance elements that you want to be evaluating, and then start to go through that process. Brainstorming is actually an important part of a process. I like to say that for a moment, the laws of physics don't apply. And so we can be starting to think about what can we actually be doing. And so they talk about brainstorming and brain writing. And so you just start to write things down and list, sometimes using sticky notes on a wall, and you can start to aggregate things together as you start to figure that out. So those are just some of the things that you can be thinking about, and you can have multiple sessions. And this goes beyond what we're going to talk about in this class. You can have more structured methods like the Delphi method for how you're going to actually do that brain writing, collect that information, aggregate it, and then come up with some conclusions based on the group activities that you're using. So having a block diagram of a physical architecture is helpful. And so here we're thinking about an aircraft control and the various components that would be related to that. And so this is a model airplane, but it's just giving you some of the examples of the things that we're trying to show in this physical block diagram. So you need to have the crew command devices, having a throttle and pedals, and then this is fed into this physical architecture for an aircraft control component. And so you can just see that this would be something that would be important that you would want to be laying out for a physical architecture. So what are the major concepts for physical architecture? It can be centralized, decentralized, or distributed. It also could be a client-server approach, depending on what exactly you're trying to do. And so centralized, there's a central location for processing control. Decentralized, so that you can have multiple sub-elements that would be empowered to do some level of controlling. It can be decentralized, where 2 or more autonomous processes with communication interfaces are designed and deployed, and then there's distributed operations. And they could either be homogeneous, that everything is identical, or heterogeneous, that there's dissimilarities among the autonomous processes. Finally, a client server. This is a software architecture that's superimposed on a distributed system. And so the client processors request the results, the server processor provides the results. And so that can be another complexity that could start to fold in depending on the nature of what you're trying to do with your system. So what is a taxonomy of single and multiple processor systems? This is specifics for computer architectures, and you can either have a single instruction, single data, a single instruction, multiple data, multiple instruction, single data, and multiple instruction, multi-data. And so historically, things were very centralized with an SISD, and now we're moving more in the direction of an MIMD, multiple instruction and multiple data. And there's a whole gambit of new processors that are starting to come out. This is already dated, but you can be thinking of Apple started to make their own processor, and so this taxonomy is definitely moving in a lot of different things, that we can be moving in the direction of easily having multiple instruction, multiple data through distributed multi-core systems and other more specific ways of viewing processor architectures. So what are the justifications for distributed system? You can be having transparency. Users need to have no insight into the system components. So there might be situations when that might be available. You can have open architecture. Additional resources can be added with little or no adjustment. Scalability, you want to have the ability to be extensible. That's always wonderful to have. Resource allocation, one or more hardware or software modules can be used to execute a task without human intervention. Concurrency, multiple tasks can be executed simultaneously, and fault tolerance. Systems adjust internally when hardware or software problems occur. So that's just some examples of things that might be coming up when you're contemplating whether or not you can have a distributed system. Well, let's talk about some examples here. I actually had some colleagues that worked on something that was part of this kind of capability that the FBI developed, and the FBI fingerprint identification system. And so basically, it's the integrated automated fingerprint identification system, and there's a couple different elements: the identification, tasking, and network segment. There's the interstate identification index segment, and then there's the automated fingerprint identification system segment. So you have these different segments that have to work together to provide this overall capability. Crossing state lines, and so there can be issues that would be things that the FBI would have to do. The FBI is a federal government entity, but you need to be considering the jurisdiction of the states and the local government as well as you're doing these things. So the request for proposal was sent out and various companies bid against that. And so what they had was this 10 print processing system, TPS. This was a key element that was identified. It could process paper cards with 10 fingerprints. Maybe you've seen examples of that on a movie or something where they fingerprint an individual, or maybe you've had that for job application or whatever reason. It's organized as workstations in a work group. It processes about 30,000 per day. It scanned, converted to binary data, and then analyzed these. And the images had to be compressed by at least 10 to 1. The average time to perform a fingerprint image compares should be on the order of 60 seconds. And then there needs to be time allowed for display of human-machine interface was 1 second for time of request. And so those are some of the requirements for the 10 print processing sub-element. So what were some of the critical design issues? The implementation of a wavelet scanner optimization algorithm. And so basically this gets into some technology and also how much of this was going to be pushed into hardware versus software. There was issues about the workstation capabilities, the server capabilities, the workflow management, and the communication interfaces. And so here is an alternative design allocation options that were studied. And so we could be thinking of a server only, a workstation only, a server and any workstation, and a server or local workstation. Those are all possibilities that could take place. Here is just a morphological box of the instantiated design options that were considered. And I'm not going to go through this in detail. And here are some things that come up in terms of design flexibility, robustness, flexibility, agility, and adaptability. These are all the things that are important to be captured as we're trying to do this kind of design process. For product platforms, the product architecture and generic components that enable many different products to be provided with substantial interchangeability. Maybe you've had a Black & Decker power tool that they have the same type of battery, so you can go from one to another. That's just an example, and there's other examples. The inkjet printers, you can easily get the cartridges. This the benefits is they reduce development costs. Can be rapid introduction of new products, rapid reconfiguration. The negatives of maybe there's a lack of a distinctive look and maybe a higher cost for design changes. In terms of the use of redundancy to achieve fault tolerance, there's a couple different ways that this can be done. It can be done in hardware and software, via information, and via time. And so here now we're getting into the functional thought process of how we deal with fault tolerance. So redundancy, this could be done at the hardware level. So you can either have passive, and so you have extra hardware operating concurrently using a voting technique. You can have active, and so you can have the detection of errors. You can find the damage and recover from errors and isolate or report the faults. You can have something called triple modular redundancy, TMR. And so you have multiple inputs and voting. And so we're showing in more details both for a regular TMR and a triplicated TMR. So TMR, 3 things come in and you vote. So 2 or more of one means you have a correct, and you can have a more complicated, but where there's a total connectivity between the components and the voter, and we can see how that could work. So this is just continuing on for TMR. We can thinking of a software implementation of triplicated TMR. Here we have active hardware redundancy, the duplication with comparison. This is a possibility. So do they agree or disagree? And so we have the second parity check, if you will, to be comparing. You can have hot standby sparing, and so you can have replicas of data, and you can quickly switch from one to another if there is an error detected. And so that's a useful thing when we're starting to consider a hardware way of dealing with errors. You can have a pair and a spare. And so this is just another more sophisticated way of having error detection and error resolution with your hardware architecture. And that's it for this chapter. So thank you very much.